You good? Can you see the screen? The
Yep, I
solving
can
method and
see
all
it.
that stuff. All right.
Hmm.
Remember, it's only forgive step four. Step four is just saying solve. It's only these three steps, man. It's always just these three steps, and I'm gonna show you. So, first step one: label all nodes and pick the one to be the ground. They already did that right here, so they picked your ground for you. Then they say, I said, try to put the ground on the bottom of the voltage source of the negative. They put the ground on the negative, so that means that it's going to be a little bit easier for you. All right. From there, um, I should have put. Actually, I'm going to make a little note here. I got to put to label currents in the book. I got to remember that for later. You're going to label currents, so I'm going to put this current going down. Make it a little bit bigger. Put this current going down. Put this current going to the left, put this current going down, and now I'll just have this current go, I don't know, I'll have it go this way because I don't know. So bam, I got my four currents. All right. So with that being said, then we can do step two. So step two says create the no voltage equations for all your voltage sources. How many voltage sources do we have in this bad boy?
Mm, two.
Nope,
One.
just one.
Yeah.
Just the one. And so you just because it being a dependent source doesn't stop me from being able to do this step. So I'm gonna say
I feel
dependent
like you
source.
said something about that though before that you couldn't do certain things with the dependent source.
You can't turn a dependent source off. That's the only thing that you have to that's the only thing that is special about a dependent source is that you can't turn it off. That's it.
Can you do a supernode with a dependent source?
Yes.
Okay.
We won't need to in this problem because it's grounded.
But you,
But let's say I had a dependent source over here, like this, like a plus minus, and let's say it was 2Vx or whatever, you would be able to
mhm.
do a supernode right around it. I've done it. There's a
Mhm.
problem that I built where it was just like that. It was a pain in the butt. If I can find it, I'll show it to you. I think it might be in my. I'll take the book down. It might be in my. It's in my book somewhere. But
So is it useful to use stuff like voltage divider, and current divider in like node voltage equations like this?
so here's the thing: you're never really gonna use voltage divider and current divider while you're doing no voltage method. There are
Mm.
moments when multiple circuit solving techniques can kind of fuse together into one, but it's rare for you to be able to do voltage divider and current divider inside of no voltage. Typically, what will happen is you'll stick no voltage into another technique. So you might be doing current divider and you'll do current divider in the scope written as no voltage method. And what happens is right now it's a little bit difficult for me to explain because this type of problem, remember every circuit has to be approached a little bit differently. This circuit right here doesn't require any sort of other technique outside of no voltage method or mesh current, right? No voltage method, we got three nodes. In mesh current method, we got three meshes, and so they both solve the same. But if I were doing like Thevenin's method, then it might be a little bit different. You see what I'm saying? It might be a little
Okay.
bit different. But it's funny enough, Thevenin's method actually won't work on this problem because it will break down. But that's not important.
Okay.
So it is literally just about the experience. And so what happens is if you look at the last chapter of the circuits book, I have one problem.
Mhm.
I literally just solve one problem like six different ways. And I think that that's honestly probably the most important chapter in the book because the other like nine chapters show you the methods, which is nice, but that last chapter shows you why you have to know all the methods. Because a lot of students they try to pick one and run with it, which is fine. You know, if you want to, so be it. I mean, I can't judge you, but I'm not a fan of that. I always tell students they should know all seven methods, and that they should particularly the first one. If there's anyone that they should know above all the others, they got to know no voltage method first, and that's just because of all my experience with circuits. But how you guys decide
Mhm.
to do it is up to you. But as you solve circuits, you'll see, oh, this circuit I can use voltage divider. This circuit I can't. And the thing is, a lot of professors are biased. Every professor is a little bit different, and so what they do is they create problems based on how they want to solve. And I'm known to do that as well. So the professors, if your professor loves voltage divider, guess what type of problems you're going to get? You're going to get a lot of voltage divider. But voltage
Yeah, he
divider is
loves.
not
Yeah,
all.
he does love. He does love voltage divider.
Yeah, no, I remember you told me.
Heard of
You told
that.
me that.
Yeah.
And that's the thing. Most problems are not voltage divider, and so he's kind of setting you guys up for failure because it's nice to have voltage divider. If you can, you should build a voltage divider. But there are going to be problems where you just don't have voltage divider, and that's just the way it works. So it is what it is. But yeah, let's handle
Yeah,
this
because you
problem.
guys see different. Yep. Okay. Alright. I'm
So we're
listening.
going to do a voltage source. How would I write the equation for this voltage source? Don't think about the fact that it's 12 VC. Just do it exactly how you would before. And instead of saying it's like 17, you just say 12 VC.
I
Oh, let's
mean,
label
wouldn't it
the.
just be? Oh
Let's
yeah,
call
label
this
the
guy
next one.
A, B, and C.
And D, those two are all the same node. I'm assuming the bottom one.
Yeah, they're all ground. Everybody on the bottom right here is ground.
I mean, so node A is just equal to 12 VC.
Yes, exactly. And that's all you have to do. VA is 12 VC. And that's how you do it. That's exactly how you do it. Because look, it didn't solve, but it's its own equation. VA equals 12 VC. And so whenever you see VA later on, you're gonna just plug in 12 VC. It's funny because using a dependent source actually in the end makes your system of equations a little bit easier to solve because it reduces it by default. It automatically
Mm.
converts A into C by default. So it seems difficult in the beginning, but it's not. So that was it. That was step two. So step two check, step one check. Now we just got to do step three. Step three says we got to do KCL on all the nodes not connected to our voltage sources. And so what we have right now, basically every node that you haven't messed with. We did node A, so I'm gonna put a little check on node A. Check. So now we got to do nodes B and node C. So let's start with node B. So I'll put node B up, and then talk to me. How would you build node B? And then start from the left. So I'll say, let's do this guy. So how would I write that on node B? The
Mm,
40.
would it be V? I mean, so VB minus VC over 30,
Okay.
right?
So
I think.
you're doing this one right here,
Uh-huh.
which is fine.
I think you should go that way, or did you mean go with the 40?
Yeah, no,
For the
do this one.
voltage.
Do this one right here.
Oh, okay, okay. I thought you said left. My bad. Well, our views are switched. So then, if you're doing that, it would be VA minus VB over 40.
Good. Now, is that whole group positive or negative?
That whole group would be negative. Wait a minute. But yeah, it's positive
Mm-hmm.
because of the way the current is flowing here.
Yep,
Okay.
because it's going into B. Forget everything else. You're focused. You're literally just focused on the B itself. So that was the first
Mm-hmm.
one. Now do this guy.
Um. Okay. It would be VC minus VA. I mean VC minus VB, I guess. Or you could
Backwards. Don't
backwards.
look at the
V.
C. Forget that.
Look at
We're
the
looking
B.
at this current. How is that current built? It start. Where does it start? Is the question.
It starts with B.
There you go. And it stops with.
C.
There you go. Easy enough. Start minus stop always. So the next question is that positive or negative? Mind you, we're talking about this current with
Is
respect
leaving.
to B.
So
It's
it's
leaving.
negative.
Perfect. And that matters. That makes so much difference because a lot of students go, oh, but it's going into C. We're not talking about C. We're talking about B. So that was the second one. Last but not least is this guy right here. So how do we do that?
It's equal to. So I think it's like that's VB. I
Mm-hmm.
guess so. It would be VB over 40.
Good. Positive or negative?
It's leaving, so negative.
Good. And how you're talking to yourself to like walk yourself through it, please continue to do that. That is literally how you do it. That is exactly how you do these problems. And so do you say, okay, the first current's going in, so it's positive. The group. Now I'm going to talk about the.
But
Now I'm
why
going
is
to.
that? So how is that VB though? If that says VC, I'm confused.
I
Yeah.
just I you know what it was? I actually the problem was written in a way where it wasn't clear on how to name these nodes, but it did tell you that this guy was VC, so I'm gonna rewrite it.
Yeah.
Rewrite it. So
I
it's
was
actually
confused
VB.
whether I say VB or if I do VC over 40.
No. You do
That's
VB.
what switches me up.
Right now, I've just renamed it. Forget that. When you name something, go with what you named it. Forget the person. Forget the professor. We're gonna go with what I named it. I named that VB, and so every time that they put VC on it, I'm just gonna redraw VB on top. So instead of saying 12 VC, we're gonna call it 12 VB because VB is actually the voltage that is touching.
Okay.
So this right here is actually the voltage on B, so I'm gonna call it VB because that makes sense. If I call it VC, then what I'm doing is confusing myself because I drew C somewhere else. But that's not my fault. He didn't put the nodes on properly, so I just kind of went with what I
Yeah,
wanted.
that's just you know me. That's what throws me left, stuff like that. Because I'm like, does that mean I'm not allowed to do whatever? So then
Oh
you
no, no.
find a common denominator.
If you need to, do it however you feel is best. However you
So
feel is best. I see you. People see students see me do that all the time. I'd be like, I don't like the way that looks. I'm gonna do this because I think it makes more sense, and I'm still gonna get the right answer as long as I follow the rules properly. But that's just how I get down. So this is the equation that we get, right?
Mm-hmm.
And then all you got to do is remember that VA is 12 VB. So I'm gonna plug in 12 VB for VA, and so I'm gonna get 36 VB minus 10 VB plus 4 VC. So automatically it's starting to shrink just because the VA converted. So I'm going to get 26 plus, actually, if I divide everybody by 4, then I'll get, is 26 divisible by 4? Nope. I divide by 2. So I get 13 VB plus 2 VC equals 0. Bam. So that's an equation. So I'll turn that purple. So that'll be my equation 1. Make some sense? So now we just need one more equation that has B and C. But look, we never did node C. And node C connects B to C. And so that's going to be where our second equation comes from. Does that make some sense?
No,
Awesome.
C connects B to C.
Yep.
Yeah, okay.
And so now we just got to do.
Just renamed it. Okay.
So now we just got to do node C. So we'll say at C. Now at C, a lot of students will mess this up.
Yeah, this is the confusing part.
This right current right here is coming from C. And so C has 3 currents touching it. It has this guy, and this guy.
And that guy.
And so let's handle them. So first we'll do this guy. So how would I write that out?
Would it be? It would be VC.
Remember, when you're looking at the current itself, where does it start? Where does it stop? Forget the fact that you're focusing on C. It's like a 2 viewpoint. It's a 2-man point of view. We're gonna focus on VC, but what that means is we're building the equation for it, which is great. But when you're looking specifically at the current, you got to go start minus stop, no matter what node it's going into or out of.
Okay, so then if it's going into, it would just be VC minus VB or plus. It would VB minus VC.
Always start minus stop.
Always start minus stop. Okay, yep. I thought when it was like we're talking about that specific node, we put that one first.
Nope, forget that. A lot of students do that. Go, yeah, but we're talking about VC, so shouldn't we put VC first? No. That current, no matter what node, look at this. This current, this current starts on B and stops on C. So no matter what, whenever you write that current, start on B, stop on C. Start on B, stop on C. It doesn't matter whether it's going into B, out of B, into C, or out of C. It starts on B and stops on C. And so you're going to write that group as VB minus VC over 30. That group stays the same. The thing that changes, and this is where the students, this is when the students kind of make it make sense. The thing that changes, that varies between B and C, is if it goes into or out of VB and VC. And so what happens is, for VB, this current is negative. And so you put the negative right there. For VC, the current is positive because it's going in. And so you put the plus in front of the group. Does that make some sense?
Yeah.
That is where that plus and minus stuff kind of comes into play. For C, it's positive because it's going in. But the group itself is still going to be B minus C because it starts on B and stops on C no matter what.
Okay.
All right.
That makes sense. All right. So then it would be plus 2.4 A.
Good. Plus 2.4. Because that's still a current. And a lot of students, they're not going to put the 2.4 because they don't realize that that's a current.
No, yeah, that was confusing me, but you cleared it up. That was what was messing me up on the thing, whether I can mix them. Which is like, but then again, I recognize that they're all related. So then VC, so then it's just going to be VC over 50. I mean, yeah, VC over 50. I mean, well, it would be, yeah, wouldn't it be plus VC over 50?
You got the VC over 50 part right. VC over 50 is perfect. But then you got to ask yourself, I like to put parentheses around it so that I kind of keep my ideas separate. The parenthesis, the stuff inside the parenthesis is how to build the current. The stuff on the outside of the parenthesis is if the current is plus or minus. So is that current leaving C or going into C?
It's leaving, so it's minus.
There you go. Boom.
0, 0. Okay.
And so this will get multiplied by 150. It's going to be 5 VB minus 5 VC. 150 times 2.4. It's a calculator moment. Let's see. Calculator. That's going to be 360 minus, and this will be 3VC equals 0. And then these combine, so I got 5VB minus 8VC equals negative 360. And that's two equations, two unknowns. Boom. I got, let's put it in purple, whatever. I got this guy and this guy. So these two are going to solve together. You see it?
Yep.
Awesome. So now I just got to solve them together. If you don't, if you do not want to solve them together, then you can just build the matrix and put it into your calculator. So it would just be VB on one branch and VC on the other branch equals, and then you got 0, negative 360, 13 on the VB, 2 on VC, 5 on VB, negative 8, and then you just solve that and solve this guy. And then you'd be good.
This is a standard system of equations.
And so here's my question. Was that any different because it had a dependent source in it?
No.